Hello, everybody. My name is Jakub, as I already introduced myself, and we are here to talk about a journey from synchronous to asynchronous and get through the, I call it swampy grounds of handling HTTP requests, something as simple as handling a request that's coming. So, as I said in the teaser, that's based on my past experience of working with legacy systems and making them more performant, but also is based on it initiated me to do this talk. When I heard a different talk from a friend of mine, from Tomasz Nurkiewicz, who's a Java champion, about reactive, Stack reactive Java and reactive programming. Tomek at some point showed a very simple graph where he showed the cost of hardware, software, and maintenance for a traditional synchronous, let's say, or traditional as we know it system. So it starts small, it builds up and builds up, and as we get faster or we get more and more traffic, the costs are steadily rising. That's a kind of a graph that we all get accustomed to. And then he challenged that with a reactive approach, where the software development cost is higher than in a traditional one, but it's pretty stable. The cost of the hardware is pretty stable. It's manageable. It's something that can be foreseeable, but the maintenance cost is getting higher and higher. And the whole talk was about how reactive programming model is more, let's say, complicated, more complex than the traditional one. And he combined those two, telling that there is something which is called a Netflix point, a point which justifies going reactive from day one, because we will reach those thresholds and we will need to scale that high, that far. So obviously, what you see on the screen is an indicative data, and the scale is opinionated, and you can challenge that well, the Netflix point should be a little bit to the left or a little bit to the right. It's not quantifiable in any way. But the question is still valid. What is the Netflix point? And this is something that we'll be exploring a bit today, trying to understand how things are running under the hood, and then if we need that complexity, or if that complexity is something that is suitable, are we crossing, or are we passing this Netflix point? So my name is Jakub Marchwicki. As I said, I work as a software engineer and a consultant and a trainer. I work remotely, which my Instagram feed just shows full of cats. But that's not about me. So what is that Netflix point? So we can paraphrase that, saying, what is the traffic which justifies a Netflix-like architecture? Because RX Java is coming from Netflix. Reactive programming stack is coming from all those major companies. So a traffic which justifies the Netflix architecture, which we can say, or we can paraphrase that a traffic which justifies a reactive architecture. And that's the question we'll be trying to answer. What's the opportunity cost? What are we gaining? What we are losing? And how we're going to tackle it. But going even further, it's a question: at what traffic? A traffic which justifies a reactive way of solving the business goals, because it cannot be a CV-driven development. We are here to deliver a sustainable software, not to improve our CV. I know people who are happy doing minimum valuable product for years, month after month. Projects are sales-driven, just small things, never hits production, but they can freely play with whatever technology. Fine with them. I know also people who are so eager in building the reactive stack, or replacing the old-fashioned architectural legacy or traditional synchronous with reactive, that they will just rewrite everything through reactive. Because once you started doing that, yeah, that's more familiar. It's not necessarily easier. And they are eager to do it at whatever means, putting their project at risk, putting their company at risk, spending 3 months rewriting things that might not even need to be written. So what we're trying to find is a sweet spot between reactive and non-reactive. And we'll do it by understanding how things are working underneath and how we can use it. Because architecture are not togglers, reactive, non-reactive, synchronous, asynchronous. They are kind of a sliders, where we have a traditional synchronous approach on one hand, and the bleeding edge reactive, and we can place ourselves somewhere on that scale. It may be derived as the number of users that we will be handling, number of concurrent requests that we have to adhere to, and that will put us somewhere on this slider. The problem I have always with reactive is that it has been a hype, and it's still a hype. I don't want to say that it's not working. It's working very, very neatly. It's much harder to grasp. If we usually tend to see that if we start Googling, reactive performance or whatever, we get to a conclusion that better performance than synchronous code on high concurrency scenarios, obviously, and it's supported by a few graphs. Well, obviously, it looks better. But then if we go into the details, we see something like this, which is kind of a naive abstraction of actual systems behavior. Like, I've built a few systems, and I've never ever seen like just sleep for a while and do nothing. That's not how you utilize your CPU. So to better understand if reactive approach is fine with us, we need to understand how is our system handling the incoming requests, to understand whether the traffic we are having, the requests that are coming, are suitable for the way we would like to build the system. So let's decompose. We can start with a traditional multi-threaded blocking synchronous application. If you think HTTP server like Tomcat, like Undertone, like Jetty, like any servlet container, by default, it's synchronous. If you go outside the Java world, if you think PHP, ASP.NET, it's more or less the same. If you say Python, HTTP, that's how it's working. So you are coming from an HTTP request, which calls the system, and then there is a thread that handles this request through all time from the beginning of requests coming in to generating a response and passing it back. A single thread, which you might say, oh, it's a very naive model, but this model is also a very powerful model because it solves us from so many issues about concurrency and so on, but, well, at some cost. So let's drill down. Each HTTP request is handled exclusively by a single thread, end-to-end. That's what you have. And then the number of threads we are having in our systems, therefore the number of concurrent connections we can handle is limited to the pool size that we have on our system. If we don't have a pool size and we can go indefinitely, well, then at some point we might run out of system threads and there will be other problems. But in general, there is a hard limit, and we can handle as many concurrent connections as we have, as the pool size. And then there is a processing time related for each and every request, which determines the throughput. If we have a single thread and we can handle just one concurrent connection, just a single connection, and it takes 500 milliseconds to handle, then we can handle 2 requests per second. That's very, very obvious now. But that's the question we are actually having to answer. How many requests can we handle? So if we do a very simple math, as I did before, we have 300 milliseconds per request. You can argue that, oh, that's a lot. That's not a lot. It depends on the scenario. If you have to call an external vendor, which is in AWS in Ireland, and you're in Germany, then 300 milliseconds for a hop trip over HTTPS, yeah, that's still a little bit slowish, but that's not something you might never encounter with. If that's within your internal network, that's a lot, but let's have numbers reasonable. So let's say we have 600 milliseconds per request, and we have 200 threads. I will get to this number, why 200, but let's leave it for now. So how many requests, how many concurrent requests we can handle? So there is a bit of magic, and yeah, we should be able to handle about 666 requests per second on a long-term average. It means that if we measure long enough, on average, we'll be handling 666 requests per second. Okay, that's fair enough. That's derived from a little low. It's a low from operational research studies. You might have heard it, the Technical University, long forgotten, and it's where real life meets with problems we are having. It pretty much can be described as your throughput is the number of work in progress, so concurrent elements you can handle through the lead time, so through the time spent on each and every request. So if we get in here, we have an average time spent on in a queue. So on average, our request is handled for 300 milliseconds, and then we can have up to 200 items in the queue. So that leads us to arrival rate. That's how it's called in the little low. So we can handle 666 requests per second. Yeah, that's the low. Very simple. So now let's imagine that we are having, to simplify that, we have a shop and we have customers arriving to the shops on the long-term average. So we try not to cluster them. They are arriving one by one. It's very good in pandemic times. So customers arrive at the rate 10 per hour. So that's our arrival rate. And the customer stays on average for 30 minutes because he is looking around and he's like talking to the clerk and so on and so forth. So the average numbers of the customers in the store at any time will be around 5. That's the little low in practice. And now let's suppose we are doing more advertising and our arrival rate raises to 20. So our store must either be prepared to host on average 10 occupants, 10 people inside, or must reduce the number, the time each customer spends in the store by half, so to about 20 to about 15 minutes, or well, we may hire another clerk. Nonetheless, we have some ways to go around this equation on very simple scenarios like the shop, on a more complicated scenarios like the HTTP handling. And this law is kind of a universal law from economy. So this is pretty much how it works. So how it works in practice. Let's get some very simple code. Let's imagine that we have this HTTP API, the REST API, where we are doing some loans reconciliation or risk assessment, and we have a very popular scenario where we have to amend multiple requests all together, and then assemble a response out of that. So we have to assess to get the risk assessment details, and get some loan details, and get some member details, and assemble it all together and return to the customer. So in an ideal world, if we try to benchmark it or measure the performance, we are aiming for something among those lines where all the percentiles are more or less nicely scattered throughout the graph. So we have like most of the requests handled in reasonable times. Obviously, those triggers are indicated. So like, okay, our average is about 1 second. That's a complicated task we have to do, and most of the things are happening in those few seconds. We have a few spikes, but nothing extraordinary. And as the throughput grows, we are stable throughout our system. That's the ideal word. That's something we would like to have. But then if we take and try to hit it with some real performance tests or some load testing, we got to weird things, because, for example, our server starts behaving like this, where 90 or 80% of requests are taking a lot of time, and the handling time is increasing together with the traffic. And then if your traffic goes down, then the response time is gradually going down. So it still holds up with a little slow. At the beginning, it's all fine, but then it grows and so on and so forth. But as a Java developer, we see, okay, that's Tomcat, and we've heard that Tomcat is not ideal word, and obviously we are writing standard Java servlets, so our servlet container is more or less drop-in replacement for what we are having. So let's substitute Tomcat with Jetty. Oh, I've heard Jetty is more performant. So we get to a point that for the same traffic, for the same scenario, we have a totally different graphs. It looks slightly better than Tomcat, but it's still not ideal. And then a friend of ours comes over and says, well, I had this friend working in Red Hat, and everything is Red Hat and is built on the top of the undertow. Let's run it with the undertow. And we are again running the same scenario with an undertow, and we got, ooh, weird graphs. What's going on? So what's just happening? Like, why this very single scenario when benchmark is giving them on each and every server totally different results? People said that it's a kind of a standard and it should somehow be repeatable. Yeah, let's see. So if we go to Tomcat, when the queue is full, then the number of connection is hitting something that is called max connection on Tomcat. So upon startup, Tomcat creates 10 threads. That's their minimum thread pool, and the numbers can grow up to 200. So as you could have seen on the graphs, it was steadily increasing. And then if the maximum threshold is reached on Tomcat, they say we can accept additional 100, and that they will just waiting. And if we manage to get the result, we'll take those from the queue. And it can go as long as we reach the max connection, so 200 connection. Why it was built that way? Because back in times, that was more important for a server to handle the traffic, to do everything possible to answer the incoming request, no matter of time. Whereas in nowadays world, and now when you see that your connection is sluggish, that your response time is increasing and your browser tab is not loading, what you do, you just hit refresh F5, and yeah, now the server has to handle the requests. So these things change, and now let's see how different servers adhere to those changing times. Because on the other side of the spectrum, we had an undertow, which performed totally different, and it's because underneath undertow, the model to handle those requests is totally different. And Tomcat, we had a thread pool, we have max threads, and we were increasing them until we reached, and there was a concurrent blocking queue on the top of that, so we could queue those incomings until we get full, and then we handled the exception that, sorry, I cannot handle that. Whereas in the undertow, it uses a totally different model for connectors. And the default configuration of that is that it runs 8 times CPU core, and these are my worker threads. So my threads for handling, for doing the job. And then there are some non-worker threads, which are more or less equal to the number of the cores in the CPU. So if we have a 4-core Intel CPU with hyper-threading, we have more or less 64 working threads on the Tomcat compared to 200 with Tomcat. That's the difference. But there are other things that goes on the top of that, because this calculation is based on this very simple. You can look it up in the source code of Underhill, that we are taking the maximum of available processors, no less than 2, and multiply it by 8. But this number of available processors on the JVM has been changing throughout times, because if you are running like Core i7 with hyper-threading, it will return 8, which is fine. But if we run something from non-Intel, it can return, for example, 4 of logical cores. But then if we run it in Docker, and on Java 8, we run it with this one CPU, it will still return 8 for a quad-core, unless we tell it explicitly to run on a very particular CPU, or we jump into a newer version of Java, or we retrofit some patches to JVM8. The thing is, this number, this figure, is a little bit misleading. And if we said run it on the first and the second CPU, it will return 2. So you can see that just by fiddling with the external environment that your application has no information about, you can drastically change the number of available processors for your working thread, which will severely impact your performance. So we are running, for example, 64, 16, or 228 threads, and compare it to 100 or 1000, which is a default for Tomcat and Jetty. And the question is, like, is it okay or is it not okay? And should I run it like this, or should I tune those defaults? Because the defaults are fine as long as we are understanding them, because they can be very, very misleading. This is one of the defaults. The other very infamous default is the default timeout for HTTP request in Java, which for a standard socket or for the standard connections is just infinity. It's just unlimited. You just wait and wait and wait for a response that might never come. So I have a few takeaways in here. One of those is that a full stack developer doesn't mean that we have the same technology on the front end and on the back end. It's the seniority that we are talking about. It's coming from understanding the layer beyond the code we are crafting. And that's exactly the point. Understand how Tomcat is working with the code we just deployed onto it, and see how it goes further. But there is more. Not all requests, not all threads were created equal. Because if we get to this very naive examples, we have certain things that can take longer, and we have certain things that can be faster. We have certain things that be more important, whereas we have certain things that we can live without. If we say risk assessment, and it's an on-demand computation, it can take up to 1 second or 600 milliseconds. It will take long. We have to calculate that. And then we have two relatively fast lookups, direct lookups to a database or something, just calling an external service, let's say 100 milliseconds or 300 milliseconds, significantly less than the risk assessment. And if we handle it through the same thread pool as Tomcat is doing that, we'll get to a point that we have a thread pool, and then we have a number of requests that is coming, that is going to those external services, and where it will be spending a significant amount of time just waiting for the response. So we get 1 and 2 and and so on and so forth. The requests are coming and we are scattering them around. And then some of the requests get stalled with our risk assessment. There was some problem in this risk assessment computation, and it's taking longer and longer and longer and longer. It doesn't scale. So as it takes longer, more requests are just waiting for an answer for this particular service, which is a very weird thing on any benchmark, because you get to a situation that you have a lot of threads. They seem fine, but they don't do anything feasible. They're just waiting, and they're just waiting for a response that might never come. So what people start to do, and that way we go to another aspect of synchronous or classical HTTP server. People get into asynchronous and multi-threaded. They were still blocking, but what they did is that they decided to decouple the handling of the HTTP requests and the handling of the actual business logic, some network calls, some other processing. And those handling of HTTP requests were blocking, but they were just doing nothing. They were just offloaded, and the rest of the call was done asynchronously. So if we get into the details, we'll see something like this: that operations can be done choosing a worker thread from a separate thread pool, which is good. So we can start to encapsulate different types of work into different thread pools on still the classic HTTP server. So the IO thread, something that handles the HTTP request, is returned to the pool and can run for other requests and process other, and processing of the upstream responses, or the rest of the call, is done asynchronously too. And then the worker thread notifies that, yeah, I'm done, and the IO thread can complete the request. And this this can offset any latencies. It can be a very nice throttling mechanism. Or we can circuit break at this time, just to keep the blocking part separate from the non-blocking part. If we get to the code, we'll get something like this: that we can do async for the loan details and then apply the result to a separate call asynchronously, and then combine those all together with the REST information, all done asynchronously. If those three calls were independent, we could have just fired one by one asynchronously and just wait for the result to come and assemble that, or we can do it more nicely with the Java future, the completable future. So if we see how those are handled on the different executors, we'll get to a situation where we have the request thread pool, and we have a dedicated risk assessment thread pool, and some other, but I'll just focus on this single one. So requests are coming and they are handled, and what happens if we are running over threads on the risk assessment thread pool? Well, we can adjust this thread pool. We can calculate the capacity based on the little low, how much time we need to spend there, and bulkhead this particular calculation. We can do timeouts, we can do circuit breaking, but the thing is, it's encapsulated, and our service is still working. Our service can still handle different requests. So there is a takeaway out of it. The thread pool tuning is deeply tied to what the application needs. We need to understand the nature of the traffic, because it's very easy to just go on the defaults, and yes, it will go worse, or it will work worse than without any asynchronicity. But if we understand the nature of traffic, if we do some basic calculations and we think how much time we do spend on different things and how much time is too much, yes, we can shape it, because then we can, if we do it badly, if we do it incorrectly, we can starve the servlet container, make it totally unresponsive. No matter how many threads we can burn them 100% just for spin looping, and just But if we understand what's going on, we can say, okay, you have just, that's lots of calculation, you have a few threads, it's CPU intensive, then it's IO intensive, you have a different thread pool, and we can adjust, we can manage our resources better. And we would like to get to a point where the handling time of our request will work more or less as a normal curve. We have an average, and those requests will be evenly spread around time. However, if we do it badly, if we don't observe downstream latencies and we don't measure, we can get to a situation like this. We can get to a situation that nothing really works, and there is a bit of fastly handled requests, and there is nothing in the middle, and there is a lot of stale requests. And it's because we haven't figured out the nature of the traffic. And let me quote again on the Tomasz Nurkiewicz blog, where he was drilling down the nature of handling the file download in pieces or as a whole. And he was drilling down each and every aspect of the problem so that he can get from 900 milliseconds to 90 milliseconds per downloading the same file. And he did it to understand the nature of the problem. And that's something that we have to understand and learn up front, and then tune the system. Because if you understand the problem, you can get much better results than just throwing more technical stuff on it. Just giving you an example, if you have a long-running query, if your service is returning, is your request running like 10 seconds, 8 seconds, because it's running a long query to the database and then doing some processing with that. And then you start thinking, how can I make it faster? Throwing an asynchronous way of working doesn't help much. But if you understand the nature of your data, and you can say, well, I can partition that request to the database and do not go with one single query, but do 250 queries, sharded by or partitioned by a certain ID or whatever, then it appears that you can assemble it differently, you can process it to the client differently, you can stream it, and you just open yourself to a whole bunch of new possibilities, how to improve the scenario, how to improve the efficiency and the performance of what you're handling. And obviously, there will be people that will say, well, just do it asynchronous, single-threaded, reactive, non-blocking, and it will be faster. Well, in some cases it will, in some cases it won't. But yeah, we are here to talk about it. So we have the asynchronous, single-threaded, and non-blocking. Yeah, reactive. So what it means to be reactive. Reactive means that there is a reactive application, which is largely event-driven. So it takes on requests, it queues those requests, and it handles them to an application which has a long-running single-threaded event loop or multiple event loops, depending on the number of CPUs. The events can be, well, a time has passed and there's a time event fired, or something arrived at the socket, or something can be read from disk, or HTTP, or execution exception has occurred. Events. Just something happens, and we are just waiting for them, listening that something did happen. And when it happens, we put it on the event loop and we do some computation on that. Computation, CPU work, no IO on the event loop. Just get the calculation and get out the event loop to take another one. So we try to utilize the CPU as much as possible. And because nothing blocks, event loop can potentially deliver a huge number of events. For example, many thousands of requests, not IO, but just handling the essence of the HTTP request. And then if something needs additional work and if the work is not returned immediately, we provide some handlers to receive the events for some further processing, like reading from the data from the socket. We get an event, data arrived, we want to read them, but we don't want to read the socket synchronously. Or we can't, we can offload it somewhere else. So a reactive system promises a few things. So if you go to Reactive manifesto, it just goes there as obviously. So it's responsive. It handles requests in a reasonable time. That's one of the expectations. That's resilient, so it can stay responsive in face of the failure. As you've seen on the graphs from the servlets, they did a lot to respond. It could have taken a lot of time, but sometimes it failed. And if it failed miserably. For reactive, it's more of a, I promise you to answer on average over a certain throughput or over a certain speed. And if I can't, I will just turn an error. I will push back on you that I cannot handle that, unless I will scale resiliently, adding more and more computation to my problem. And then I can be elastic, so I can scale up and down, and be able to handle more traffic, more load with the minimal resources. And I'm as a system, I'm message driven, so the interactions are asynchronously message passing, the events passing here and there. And the thing is that a reactive system does not require a reactive programming model. So reactive programming model, Eric's Java, Project Reactive, that's one thing. And reactive system is the system that can fulfill those scaling independently. So on the top of a completely synchronous reactive, completely synchronous programming model, we can build a reactive system, for example, utilizing different queues and buffers around it. So we just need to understand what the problem we are trying to solve. There's a reactive programming in the technical terms as handling huge volumes of data in the multi-user environment. We get some efficiency. We have the same number of CPUs, same number of caches, same level of caches, but a few context switches, because everything that is CPU heavy is on this event loop. So we can get, for example, 25 increase in throughput on the same hardware, and even reducing the utilization. So what we get is we get more traffic, right? But the cost at which we get this more traffic, and the paradigm shift that we are changing is huge. If in our application we used to do thread local context, there's no more thread local, because our thread that we are using is not local anymore. It's not ours. If we don't use it, the system will take it and there will be somebody else using it. So yeah, no exclusivity. And the tooling around it, it's mature, but it's not there yet. It's for different purposes. So if you say, well, I am in Java and there is a reactive database connector, I can use it. Well, yes, you can, but database pulls, that's something new for them. And that has been there a few months ago, even. So it's not just drop-in replacement. It requires understanding what you're doing and doing it right. If we get to the code looks more or less as it's used to with the asynchronous code. That's an Rx Java representation of what we had before. So we say we have a single this, so single response coming, and then we zip it, we assemble it all together, and we take an observable to return. But this promise is a paradigm shift. So our blocking systems were fairly easy to grok and debug, and the threads were doing a single operation, which was great. And now the event loop and now we have this event loop that now it's doing this, and then it's doing that, and then it's doing something else, and the stack trace coming from it is a complete meaningless gibberish that it's hard to grasp for us. And then if we don't handle the connection, it'll just go somewhere. And yeah, we might not even notice. The thing is, we want to get this performance track, but at what cost? Because we used to do things like this: synchronous, naive, procedural. But when there was a problem, we obviously knew where it was. Now we are changing the paradigm. We get into something less familiar. And this is something we got when Java 8 streams arrived. People say, well, it's less readable. Well, it's not less readable, it's just less familiar. So we get the same stuff done with Java 8, and then we can get the same stuff done with Reactive or Java. We can do observable and do synchronous or asynchronous operation. The problem that we'll be facing, and that's something the first and the most problematic thing that we'll encounter on stepping up to this reactive ground, is that for this simple, very simple code, we had a stack trace more or less like this, where we more or less knew where was the problem and what was so problematic. But when we get to reactive word, the same code will start getting us very, very different examples. So very, very different exceptions. So this is very straightforward. It tells us you made a mistake here. But this very simple code, complete code on Java, will return an exception like this. Notice that there is no reference to my code in this exception whatsoever. Yeah, that's a very, very unfamiliar thing for people. So another takeaway. You might notice, you might not have noticed, but both WebMVC, servlets, synchronous programming, and web plugs, RxJava, Reactive, have reasons to exist. And we just need to understand what's the tool best for. So getting back to the original question, what is the Netflix point? Well, the general answer, a perfectly consultancy answer, will be, it depends. It depends on things like, do we know our clients and their user flows? So do we know how the users will be using our application? Do we know their expectations? Do we know what we are optimizing for? Do we know the domain? And do we know the opportunity cost, whether it's worth or not? Because it's very easy to jump on the next technical solution, but as you can have seen, getting through different aspects of handling something as simple as the HTTP request can bring different examples, different scenarios and different problems. So not only understand what we are building for, but also understand what we are building on the top of, and then we can be successful. Thank you very much.
Well, I find it really, really insightful. So I very much enjoyed the way you gave this food for thought. That it's really important to understand what's under the covers.
Exactly.
And okay, reactive is useful, is probably also fashionable, but it was designed for specific scenarios and with a specific purpose in mind. So you have to understand the thing because before just jumping on it and using it, right?
Exactly. And if you don't do that, I can't say you can't do that. You should, because that gives work for me, for people like me, for people like you, that people come to and saying, well, we have this everything reactive, and we don't fully understand what's going on. And then yes, then we can step in and help. But in the essence, it's just choose your hammer wisely, and then it'll be all fine.
Mm-hmm. All right. And we've got someone in the audience who's really appreciating the way you explained everything.
Thank you.
And the question was, should I understand that the key takeaway is to analyze the request traffic in order to know where / how to optimize the backend system? This is one of your key takeaways.
Yeah, I think that if somebody comes to you and say your system is not performing well enough, or your system is not performing, the first thing you should do, or you must do, is pull out your Grafana dashboard, if you don't have, install it quickly, and understand how the traffic works. Like how many requests are coming, how much time you spend per request on average, how much time of that is going for downstream dependencies, for the database calls, and so on and so forth. Once you grasp it, once you have this whole picture, then you can, then it's not like a big giant knob that you have to twist. There's like a bunch of nodes that you can twist here, and then you can get performance. Obviously, you might get to a conclusion that what you're actually doing is passing data from one side of the system to another, and reactive non-blocking will be ideal for that. If that's it, let's go for it. But understanding what the system is doing is crucial to be able to make any other decision. That's going to be a key takeaway.
Mm-hmm. All right, and one more, and we're done for today. A lot of appreciations and applauses.
Thank you.
Your audience on the channel. But the question is, what's your opinion on where GraphQL fits the best? This is quite of a topic, of course, but I don't know. Maybe you can give some quick.
I've been using GraphQL in my current environment. It fits nicely as a kind of a gateway from between the front end and the back end. So we have a set of services, and from the backend perspective, we don't need to handcraft each and every request for different scenarios. But people on the front end side doing the user experience can tune up what they are getting to their needs. That's obviously a nice thing. That it comes with a certain, maybe not drawbacks, but potential problems. Is now the part of the system is in the, we just a few days ago had a discussion whether GraphQL layer in our environment should be managed by the front-end engineers or the back-end engineers, because we do have a different approach in mind in terms of monitoring, in terms of tracing, and so on and so forth. So who should be handling that? And then how you are optimizing that, not to overfetch or not to underfetch, and pretty much how to tune in the GraphQL. So if you are working in an environment that you are setting up lots of API gateways, GraphQL might be something for you. If not, that might just help you tune the or handcraft the data to whatever front-end needs, which may also solve the problem. But then you have to understand all the problems that enterprise integration brings in, because what GraphQL does is a few of enterprise integration patterns. So if your GraphQL is handling 2 requests from 2 different data sets, what happens if one of those is not responding fast enough? Are you returning whatever you have? Are you returning a partial answer? Or are you just returning an exception and a 503 error? These are things that you have to understand, again, depending on the nature of your data. So pretty much getting back to what I said in the presentation, know your data, know the nature of your traffic, know what you're doing, and then you can easily pick up, well, that's GraphQL and it fits me.
Jakub, brilliant conversation. Thank you very much for that.
Thank you very much.
Looking forward, well, to the next time when we hopefully can meet in person.
Yes, well, I will love to come back to Romania at some point. I have this picture of this wall picture to take a photo and have it on my background as well. So yeah,
Okay,
I hope next year.
let's do that. Thank you so much, and until next
Thank you
time.
so much.